So today we have 6 very interesting and very presentations from excellent scientists. All of them, they are excellent scientists. We are going to start with one of the local hosts, Professor Lanzani, who is professor in physics here in Polymer and also director of the Italian Institute of Technology here in Milan. Professor Lanzani, apart that he's an excellent scientist, he's an excellent ex-basketball player, or he thinks so, and he's an expert in time result spectroscopy. This course will be a full course on IPEN Moodle platform after the end of the project. So this is like just to take a flavor. He has prepared all the presentation about the full course. I will upload them, but it's not going to be accessed by you until the end of the project, that we're going to have the videos, the demos, and everything. So, Professor Lanzani, thank you very much for the honor, and the floor is yours for 45 minutes. 10 minutes before, I will notify you.
Good.
Okay.
Thank you very much, Kostas, for the introduction, for the organization of everything. You're an excellent coordinator, saving us. Okay, so today, you see I have a double laser with a beam splitter in... No, it's not true. The topic of today is pump probe. So I'm going to talk about this technique. It's a basic tutorial, so do not expect any fancy result. I start with some history. So we talk about time resolution, right? So this guy, Muybridge, I think Muybridge, was an expert in photography, and this is the guy. See, he invented. I have this special effect. You see, I like this. So what he invented? He invented a shutter, right? So with some rubber and spring and something. And he could open and close the shutter in 1 millisecond. At that time, that was an achievement. And it was a disruptive technology, changing photography, because before this, you had to stay there for minutes to take a picture. So that's why the picture looks so strange, right? That you could not move, and any motion was giving some blurring of the image. So with the fast shutter, things were changing. And now Stanford, the guy who established the Stanford University, whose son unfortunately died in Italy, actually. It's a dangerous place. I mean, so that was in the name of his son that he established the Stanford University. So Mr. Stanford was very rich, was making the railway in the United States. So he asked Muybridge to solve a question that was been open for many centuries, about the aerial phase of the galloping horse. So how are the feet of the horse when it is galloping? And indeed, so he discovered, where is the most, here is this one, let's do the other one. This is the main result. Are you shocked? I mean, that's the main result. I see, maybe you don't. No, the reason is, number one, there is an aerial phase. So there is a time in which the 4 feet are above the ground. Number two, if you look at many pictures, say painting, the horse is always made with stretched legs, because the idea they had was that it was stretching the legs when it was running, and not in this position. So he found out that in the aerial phase is like this, the 4 feet above the ground, but aggregate, say, clustered under the horse. So that was a big result. How he achieved this? Well, he had 40, I think, camera, and the horse, there were very thin, say, forgot the name, say, strip of some I think it was silk or something. So the horse was going and activating the shutter one after the other, and so the camera was taking the picture. So it's a stroboscopic, not technique. So each picture is taken in 1 millisecond. That allows you to time resolve the phenomenon, right? Because you take picture at a very fast rate. So that's the idea of time resolved spectroscopy, essentially. So we start with 1 millisecond, then we went down in time resolution. Now, just to complete the story of the galloping, I should tell you that the elephant doesn't have an aerial phase. Okay, that is expected because it's so heavy. So you see there is always 1 foot on the ground. And this was established much more recently, 2003, and it was published in Nature. So now when they reject my paper and they say it's not interesting, I say, okay. So the elephant doesn't have the aerial phase. Now, so the basic concept of pump probe is like the start and stop watch. Now here there is another interesting thing that you see, even like the shutter with Muybridge. So you need the t equals 0. So you need a shutter. So you cannot measure a time evolution of a system which doesn't have a clear starting. So that means that you always generate a coherent state. Then this state may evolve in a totally incoherent way, which is most of the time, or it can preserve the phase and give you some specific coherent observable. But in any case, you need to have a certain instant of time when there is a t equals 0 and there is something that is perfectly aligned in a sense, right? So then you can start to do the measurement. So the stimulus, which for us is the pump, what we call pump pulse, it will be optical, is the one that makes a non-equilibrium state of the system. And then, this is a collective state. Then there is the probe. The probe is any things that you need, that you use in order to interrogate the excited state. So that's the idea of the experiment. At t equals 0, there is the impulsive excitation. Impulsive means on a time scale which is much shorter than the event, than the phenomenon you want to measure. And then you start to count the time, the clock starts in ticking, and at some point the probe arrives. And that is fixing the time delay, right? And the probe is like the shutter, so it's observing for a short time, which gives you the time resolution. In a pump probe, as we understand, which is an optical experiment, the pump is an optical pulse which is absorbed and redistribute the population from the ground state to the excited state. And then there is the probe, which is typically measuring new transitions which are occurring following the excitation of the pump. So these are transitions that were not present in the ground state, in the dark, say, without the pump. So now let's look again at the optical example. So the stimulus will be an optical pulse and the probe will be an optical pulse. And here I think I lost some part of the equation. Okay. The typical experiment, the experimental setup is this. So you have a laser beam which is usually tuned. So we use nonlinear optics to change the color. Like here there is an example, there is a second harmonic generation. You get a blue pump. And you get, there is a white light generation. I think you heard about this. And you get all the color. Then the two beams are focused and on the sample. So there should be a coincidence in space and time in order to do the experiment. So typically, you see you have a delay line, which is simply a mirror moving, which is changing the optical path of one of the beam. And typically, it's the pump, because you don't want to disalign your system, while the probe goes straight into the through the sample to the detector. And then you can measure the whole spectrum, which is what we do nowadays, or you can measure one, say, wavelength by wavelength, which was what I did many years ago when we start. Now keep in mind that the laser is not sending a single pulse, the laser is sending a train of pulses. So the real experiment is actually a repetition of many times of the same experiment, the same event. So you say this is the pump pulse train, and then there is usually a modulation, so it's like a one pulse on, one and off, on, off, on, off. And then there is the train of the probe, which is the same of the pump in most of the situation. Let's assume it's kilohertz, for instance. So that is 1 millisecond each the distance. And you see that there is a small delay between the pulse pump and the pulse probe. And this is your time that you do the measurement. So you fix this delay and you repeat this experiment many times. The pump comes and then the probe, pump, probe, many times. And that is give you an average, which is what you are measuring. Then you change the delay. Now, what is the advantage of this technique? Well, is that the detector can be microsecond, millisecond, can be very slow, it doesn't matter, because you do a time integration of these events that are repeated. The time resolution is just given by the delay between the two pulses. This is a correlation technique. So the only thing that matters in time resolution is the pulse duration. It's not the ability to sense electronically a delay, which is a big advantage. Because if you do, especially it was in the past, but say now electronics is quite fast, you can easily go below 1 nanosecond, but when they start it was not like so. And anyway, below 1 nanosecond is still far away from 10 femtosecond we can do, or even attosecond we can do with optical pulses. So it's a very, say, smart idea to use pulses. Now, if, say, in general, what we do here is to measure the optical property of a material that has been photoexcited. And so it's a modification of the basic property. That means it's a third-order, nonlinear third-order technique. So there is a chi-free response, which makes things a bit complicated, right? So because say, we are measuring a change in the linear property. And now I will show you better where it's coming from the story. Now, you can simplify this, however, and I'm going to give you a set of equations which are very simple, which are the one we really use for material most of the time. Say the pump pulse is interacting with the material, and this is a linear process, so we describe this as a first-order susceptibility, and there is a polarization which is formed, and this polarization coupled with the field once again. So you have two fields, two electric fields. Square is an intensity, it's a number of photons. This generates a population of excited state in your sample, okay? So that's the pump. Now, if you can separate well in time the pump and the probe, then the nonlinear formalins become much simpler. Let's see why. Now the probe is coming. The probe is also interacting with the sample through a linear process. But now, when you modulate and change the population, you add the delta n, a change in the ground state population, also the linear response is changing. And you see that you can write this as the original linear response plus a modification, a change in the linearity. And this is a sort of effective linear approach. Now, altogether, you see inside this delta n, there are the two pump fields. And here there is another field, which is the probe, and it's a polarization. Then you need another field in order to have a signal, which is P dot E. So it's a 4 electric field signal that I'm measuring. That is a third-order nonlinear process. But we don't care about this. We do things much simpler. So if you want, formally, this stuff here is a third-order nonlinear susceptibility, but I don't care. But for me, this is simply a linear response of a non-stationary state. And that is an effective nonlinear response, which is much easier to be rationalized. Now, what we use usually is the concept of cross-section to talk about absorption. That's another thing that is quite interesting because it's very simple. The cross-section of a molecule is like a target. So what I do is I throw bullets, like arrows, these are the photons, and I will throw a certain number of photons per unit area. What is the probability to hit a target? Well, it depends on how many targets you have, no? Right? So you have to count how many targets you have, and you will see that some of the photon will go through and some will get catch by the target. So if you have a number of photons per unit area and unit time, and you have a number of targets, you can easily work out the effective area which is catching the photons. That's absorption. That simply gives you the probability of absorption. Then, of course, inside the cross-section, there are the wave function, there is the dipole moment, there is the oscillator strength, if you want. These are all connected. But that essentially it's a very simple way to picture the absorption process. It's interesting that the cross-section is always a bit smaller than the physical size of the molecule, because that, I think, would open up interesting concepts of how can a molecule have a larger area than the physical size. Now, alpha is the coefficient which describes coupling of the electromagnetic wave and the material. And it describes if the energy goes from the field to the material or from the material to the field. When alpha is positive, the electromagnetic field is depositing energy into the material. It means we go from I to J. That's the absorption transition when a photon is coming. These are stimulated transition. And then this is positive. You see that the sign of alpha, of the coupling constant, depends on the difference between these two populations. So in most of the situation, the population of the initial state is larger than the population of the final state, and you get absorption. But in situation in which you have population inversion, of course, it's the other way around. And then this coupling constant become negative, and that is what we call gain. And Nj is larger than Ni. Okay, so this is the absorption coefficient, most of the time we call it. This is the cross-section, which is a positive quantity, and that's the population. And the absorption will be the final absorption of the material a superposition of all possible transitions in your sample. Of course, you have to take into account that, I mean, if Ni is 0 and Nj is 0, then you may have empty level. Of course, they do not contribute. That's absorption. Now, once again, keep in mind this, that most of the time only the ground state is populated. That's the approximation that we do. It's not always true. I mean, if you change the temperature of your sample, in particular, if you rise the temperature, also some excited state will be populated. This is changing a bit the story. But most of the time, the ground state is populated, is filled, and all the other states are empty. That's what I assume here. Now, this is the absorption, I told you. And now this is what happened when the pump is coming. The absorption is changing because the population are changing in the level. And the change in the population is the difference pump on, pump off. Okay, so that's the population difference that you are inducing in the sample. So the pump redistributes the population, and in each level there may be a change. Again, there are simplifications. If I use the approximation of before, most of the time the change in the population is simply the population induced by the pump, because originally the state was empty. So it's like the pump is placing population in an excited state, which was empty before. That's, I mean, if you want to be very formal, you should always consider the difference, but most of the time it's just the one induced by the pump, except for the ground state, of course. That's true for J different from 0. For the ground state, it's not like this, because the ground state is always filled. You will see the difference. Now, what we measure is transmission difference. So to get to the final signal, and then I'm done with all the same little mathematics, we have to consider transmission. Now, this is transmission. And the change in transmission will be the transmission with the pump on minus transmission with the pump off. That's what we call transmission difference, which is what we measure in pump probe. So we measure the difference between the pump on and the pump off. And then when we normalize this quantity, delta T over T, what we get is this expression here. Okay, so it's just depending on the change in the absorption coefficient that I showed you before. So delta alpha is what we're going to measure, the change in the absorption coefficient due to the pump. And now, because most of the time delta alpha is less than 1%, than 10 to the minus 2, we can approximate this expression here to this. So you see this, it's very simple. What we measure, transmission difference, that's what you measure in the experiment, is the normalized transmission difference induced by the pump, is simply the product of your change in the absorption times the thickness of the sample, or the penetration depth of the pump if the sample is very thick. Okay, so that experiment is, in this way, it's relatively easy and simple. What we measure is delta alpha, and delta alpha contains the change in the population. And if I again adduce the assumption that is most of the time is just the population of the state because it was originally empty, you see that the expression for delta T over T is fairly easy. It's like this, in which I did another approximation, which is a practical rule. Instead of writing this complete expression here, I take each of these terms separately and I put a sign in front. That is a practical thing that now I explain you. It's very simple, that makes the story easy. If you go from I to N, so if you go up, it's an absorption, and then there is the minus sign here, and it will be a negative contribution to your delta T over T. That means it's photoinduced absorption. If you go from I to N downward, it's a stimulated emission, then there is a plus, and that will be a positive sign. So that means transmission is reduced or transmission is enhanced by the pump. That's what we measure. So in a pump probe, essentially you only have two kinds of signal, positive and negative, or which is positive is these two contributions now I'm going to tell you, and negative is the photoinduced absorption. That's it. So delta T over T can be positive or negative, and this has a different meaning. Let me show you. For the photoinduced absorption, always give you a negative contribution in delta T over T, and you see it's given by the change in the population in the state and the cross-section of the transition. And that's the way you can reproduce your data. Stimulated emission is positive, opposite, and again there is this is a number, or if you want is a spectrum, so it's a spectral shape multiplied by a kinetics, which is a population. That gives you the stimulated emission in your sample. And finally, bleaching. Bleaching is a bit more complicated because the ground state is always populated, so you cannot do the approximation. It was emptied before, of course. Then you can really take the difference between pump on and pump off. You see here there is a minus, but this delta n is also negative because the population is reduced in the ground state by the pump, and then overall this is a positive contribution. So delta T over T positive is also due to depletion of the ground state, so what we call photobleaching, which is an enhance in the transmission. So the sample become more transparent because of the photoexcitation. Overall, a spectrum of pump probe looks like this. You see you have negative and positive peaks, which represent the two phenomena that I told you. And you can fit this spectral shape here with this simple equation, which is a sum over all the contribution that I told you. So for each peak, there is a cross-section, which gives you the spectral shape, and there is a kinetics, which is described by the population delta n. That's the spectrum of pump probe. Now, about time resolution, there is a bit more, another detail I should tell you, but it's early morning, so you can follow some simple mathematics. The time resolution, the story is like this. The probe pulse and the pump pulse are not delta, right? They are not infinitely short. They have a time duration. Now, the best thing is to study a phenomenon that is much slower than this time duration, so you can forget about this. That's the easiest thing. It's the more reliable, I would say, in the experiment. Sometimes you cannot. Sometimes you are measuring something which is more or less the duration of your pulse. So then things become much more tricky in the analysis, and noise in the measurement can cover, say, the real signal. Anyway, the real signal is what I showed you before, correlation with the probe, because the probe has a time duration, which I was forgetting before. So there is a time duration of the probe, then I take the correlation in time. And now about the delta n, the change in the population, this is described by simple rate equation like this, in which there is a generation term and the recombination term. And the generation, if it is due to the pump, will include the photon flux of the pump. And so you see the time duration of the pump is inside the generation, is inside the population delta n. And the time duration of the probe is here in the probe pulse. So overall, the delta T over T signal, because you see, so this is delta alpha, right, altogether. So let's call it delta alpha. Then overall, delta alpha correlated with the probe is your signal, and delta alpha itself comes from the interaction of the pump with the response function of the material, so it's the convolution. So you have always to take into account the duration of the pulse. A simple mathematics show you that essentially the signal is given by the convolution between the response function, which is what you want to measure, this is the population dynamics, and the cross correlation of the pulses. And the cross correlation of the pulses is this term here, is the correlation between the pump and the probe, and is the time resolution of your experiment. So now, to recap, most of the time I forget about this and I say the correlation is a line, it's a delta, and the probe is a delta, and I'm measuring something which is much longer in time. So the dynamics, the kinetics of A, the response function, is much longer. But if it's not like this, you have to do this integration in time in order to be more precise, to take into account also the shape and the duration of the pulses. So remember that the time resolution is the cross correlation between the pump, or say, is the correlation between the pump and the probe pulse. This is the time resolution. And your signal is the convolution between the response function and the correlation of the two pulses. Okay, that's for the time resolution of the experiment. Here is an example of two extreme situations. If the response time is too fast for your setup, what you measure is essentially the resolution of your experiment, like is the response function. You don't get any information on the material, it's too fast. If on the other side, the response function of the material is infinite, so it goes to the excited state and never decay, then you have a rise which is following the correlation of the pulses, and that's something, a plateau that stay there forever. So that's are the two extreme situations. Sometimes you are, of course, in between. So you have a rise time, and then you have a fast decay, and then you have to be careful. If you get a symmetric shape, well, it means you're not really measuring anything. Then there is people that still go inside the shape and knowing the pulse correlation, extracting information. But personally, I do not believe people that report time constants which are shorter than the pulse. In principle, if you have zero noise, you can do this, because you see the mathematics, you can. The correlation is changing a bit, but it is never zero noise. So I don't believe it's much better to make shorter pulses. You want to measure something faster, you go with the laser, which has shorter enough pulses. If your pulses are too long, you go to look for pulses that are short enough. Let me give you some example. In conjugated polymer, like these are like large organic molecules, you get three kinds of photoexcited state. Single state, triple state, and double state, which are the charges. You have many others, actually. I've been working. I have two lives. So in my first life, I was doing a lot of pump probe on this kind of system. In my second life, I do other stuff, biomaterials and bioapplication, always with light anyway. So I spend a lot of time inventing all possible others. So probably there are 10, 15 possible photoexcited states, but those are the most important ones. You see, each one has a specific fingerprint in spectroscopy that you can use in a pump probe experiment. So if you generate a single state, you will find that the ground state is depleted. And now we know that there should be a photobleaching. The ground state is less absorbing because some of the states are in the singlet excited state. If there is a single state, then you will see a new absorption, which was not there before, because now S1 is populated, and you may possibly see a stimulated emission down again from the excited state. If you generate a triplet, you have similar property, and you also have the bleaching. I don't put the pump here because the triplet state usually not directly coupled, right, with the pump. So it is formed after, say, from the decay of the singlet typically. But you still have bleaching, you still have triplet absorption, triplet absorption, you get eventually phosphorescence, but that is the cross-section of this is very, very small, and you know that the signal is the product cross-section population, right? So even though you have a very large population, if the cross-section is too small, you don't see anything. And finally, if you have a charge that you can form even optically, again, you will have photobleaching because you are depleting the ground state and new absorption coefficient. Typically, the charge has zero coupling to the ground state, so you don't see stimulated emission. And that's an example. This is great. I forgot the reference. It's a Physical Review B, I think. This is a test book case which happened once in the life, and is my best experiment in pump probe. That is a polymer, it's methyl leather type polymer. Now here you see everything. In this spectrum, there is everything you want to see. So you pump the material. Of course, the formula that we use to interpret is this that I told you. And you see, we pump and we generate singlet, triplet, and doublet, everything. So we see bleaching. Here it is, a positive signal, you see. There is a peak positive where the material is absorbing. That means the material is less absorbing from the ground state, okay, because it's photoexcited, so there are population in other states. Then you see two in red, two fissures. This is a positive peak, and this is a negative peak. And now this is in wavelength, so this looks like much broader than this. Actually, they are comparable because it's wavelength, not energy. Now, these two are stimulated emission and photoinduced absorption from the single state. How do I know? Number one, this spectrum here overlap with photoluminescence, and stimulated emission should look like photoluminescence. Number two, this state here and these two spectral features have the same lifetime. You see here the kinetics in time. This is time. You don't read it, but it's time in picosecond. And you see how it's going down. At stimulated emission, photoinduced absorption, they have exactly the same kinetics. So they decay the same way. Probably they come from the same state. So this is a signature of the single state. And they are formed immediately. Then there is another band which is appearing here, and it is very long-lived. It's still there after 400 picosecond. And this band has a different kinetics than those two. So this is not a single state. What it is? Well, if I do a chemical doping, which means I insert or take away charge, so I induce charge photoexcitation, I see exactly the same spectrum. This is the doping-induced spectrum, and this is the photo-induced spectrum. You see it's the same position, the same shape. So that is a charge. So it means that a part, say, say some fraction of the excited state is forming charges. So we have single state, neutral, charges, and then there is another peak here, which is interesting, is there from the very beginning, but is obviously taking over. Say, you see, is the largest at 400 picoseconds. Is a long-lived state, which is appearing at, say, below 1 micron. That is exactly where, from other spectroscopy, you see the triplet is absorbing. So this is a triplet absorption. So I get everything, triplet, singlet, charges. That's unusual. I mean, most of the time, you have everything on top in the same position, and it's very difficult to understand what is going on. But here is a good example, and you see you can perfectly reproduce this spectrum using this formula. This is each sigma is the shape of the peak, and this is the kinetics that you put in the population. So it's very simple. Now, in general, we describe the population with the rate equation, which is a very powerful tool, even though it's relatively simple again. In a rate equation, you get the dependence in time of the population, which is given by a generation term, and the recombination, a decay term. So the generation can include a direct optical pumping, which will be related to the ground state population and the cross-section for absorption, or a decay from some other excited state. That is populating your state. And then you get the decay, and the decay is usually an expansion over the population itself. So you have the first term, monomolecular, the second term, bimolecular. Then you can have Auger, you get many other population. Now, the monomolecular decay is the one that is linear in the population. How do you distinguish this experimentally? Well, this is a kind of decay that does not change if you change the intensity of the pump. Okay, so you double the intensity of the pump, you make one order more excited states, and the decay is over the same. That's monomolecular. And it can be a constant, so a fixed time constant, and the decay is exponential, very simple, or most of the time it can be dispersive. So there is a rate, there's not a single time constant, there are many time constants, there is a time dependence, and then you get typically a stretch exponential decay. The stretch exponential is a nonlinear, is like the crack in the wall or this kind of thing, those kind of phenomena that start fast and then slow down in time. So this describes most of the time a real story. This is relatively rare to be found because it means you have one single lifetime, constant, fixed for all the time. It's unusual. That's the molecular decay. The bimolecular decay depends on the square of the population. So it means it depends on the encounter of the excited state. If you double the excited state density, then you have a faster decay. So this is strongly intensity dependent of the pump. So you pump more and the lifetime becomes shorter and shorter. That's a typical indication of bimolecular process, not the shape, not the kinetics. You see here again that you can have a constant time. That means that you always have an equilibrium of your system, or you can have a time-dependent decay, which is very common. 1 over square root of time is very common. It means the process is slowing down. That is much more common because I tell you immediately how it is. If you annihilate among each other, well, it's not very nice. So what happens here, for instance, here I have a very dense group, so they will disappear sooner. But here, those are far away, so they will live much longer. So I do not have a constant lifetime. So Costas is quite isolated. He will stay here longer. Before he encountered Stefano, and finally they will annihilate. And we don't want to know the detail of this. So that's why most of the time bimolecular decay depends on time. Of course, if every time there is an annihilation, the system reorganizes very quickly, then I always have the same situation, then it's constant. Here is an example, is an historical example. 1997, you see, first author here was young. I published this work on sexy thiophene. I think no one cares. Maybe is what is called the sleeping beauty. So it's still waiting for a booming in the references. Anyway, what we found is clearly a time, the intensity-dependent decay. You see that the decay becomes faster and faster. You see here that the measurement is extremely noisy because I think I was using a very noisy laser at that time. Anyway, and the way we could reproduce these kinetics is assuming a square root, 1 over square root of time for the bimolecular decay, and also some kind of molecular decay. So that's an example. This is another example. You see now this is this is 2003. The laser is improved, and Larry Luer was taking the measurement, probably was better than me, and the signal to noise ratio is much better, but you find the same thing, that the bimolecular decay depends on 1 over the square root of t, and there is some diffusion constant which is describing how the single state meet. Then I want to make a point, which is, I think, curious and interesting. When the constant here does not depend on time, you have a Markovian process. That means that the probability depends only on the density, on the situation at that time. So, for instance, if you look at these two traces, the red one, you see that this one has a much higher initial density, so at the beginning is much faster. But when the density of the first trace reaches the level of the second one goes perfectly on top of the other, so the decay becomes exactly the same. If you have a non-Markovian process, the decay at a certain time depends on the history, because the non-Markovian process has a dependence on the distance in time from the origin. So what I showed you before was a non-Markovian behavior. That means that the same excitation density in this situation and in this situation give me a different decay time. So here is slower and here is faster, but the density is the same, the population is the same. The reason is that because it is non-Markovian, there is this time here, and this time is a clock, is measuring from t equals 0, right? So it is a difference. It's not just depending on the population, it's depending on the history of the system. So that's an interesting observation. You can also measure other quantity like mobility, and that is very interesting. Mobility is something that you want always to know about application electronics. It's not very easy to be measured, especially on a short time scale. You can do in some situation with pump probe. Now let's assume Langevin recombination, nothing new, 1903. So the Langevin recombination is a process in which plus and minus charges are distributed in, and they have a mean free path that is shorter than the Coulomb radius. So that means they are under their Coulomb, mutual Coulomb interaction. They feel each other through their own electric field. So in this situation, the decay of the population is bimolecular. So it goes with there is a bimolecular coefficient gamma, which is multiplied by a population to give you a decay. And but it depends on the field. And now the nice part here is that the bimolecular coefficient contains the electrical mobility because the charges are moving under the electric field. You see here that the equation is quite simple. So what you do, you make a sphere with the Coulomb radius, capture radius. It means that if the distance is below this radius, the charge will annihilate and recombine. And on this surface, you are considering a flux of charges coming due to a drift current due to the field. So if you do this simple equation, then you get with the bimolecular recombination, and there is this relation between bimolecular constant and mobility. And indeed, that's what we did. This is again a measurement done by Larry Luer. You see here the decay is faster or slower at different population density, and you see we were measuring the bimolecular recombination of charges, but the bimolecular recombination of charges give you information on the mobility because there is an electric field. So we were able to measure the mobility of the charge after 1 picosecond from their generation, which is something you cannot do with an electronic measurement, with a transistor, with whatever you want, space charge field, whatever. There are many approaches. No way that you measure in 1 picosecond. Even fast photoconductivity cannot do this. So it's an interesting information. Actually, on those time scale, you always find relatively large mobility, which become 2-3 orders of magnitude smaller at longer time because scattering and other processes are starting in. And then I have another example. This is more new. This guy is the king of the long distance shoot, because 2 days ago we should show Costas what he did. He was very far away, he was doing like this and making a perfect basket score. Of course, you understand that one that is throwing like this is not a good player, but anyway, but he did it. So, yeah, well, I think he plays soccer. So. Now, we were studying an old friend. I lost my nice, it's back. And so we are studying an old friend, which is azobenzene. Azobenzene is a photochromic molecule, and it's the kind of molecule that goes from the trans form to the cis form when you shine light. Very well known. And you see the spectrum on the top, you see that the absorption spectrum is changing. When you shine light, the trans population goes away and the cis is formed. The cis is absorbing here and here, as a much smaller cross-section as the trans here. You see the population dynamics here is pretty slow. It takes seconds to generate a measurable population of cis isomer. All right. And now, let me look at this. Now I have to speed up. What happens in this molecule is that when you put the molecule in water, the system is totally locked, and it does not rotate anymore. There's no more isomerization. When you put it in a good solvent, it is, however, isomerized. And what we do, we put them in the cell membrane in order to stimulate cells, and there they still move. Now the question here was, how long does it take to rotate the molecule? It's not the second that I showed you before. That is the population, the ensemble information. But the single molecule is much faster. How do we measure this? Well, you should remember what I told you about the train of pulses. When you do the pump probe, you assume that between one pulse and the second pulse, the system goes back to equilibrium. If this does not occur, you cannot do the pump probe. So in order to measure the system that go from trans to cis and stay there for a second, you need to do a trick. And the trick is to circulate the sample in order to have always a fresh trans molecule that is intercepting the pump. And that's what we did. And so circulating like this, we could measure the dynamic of the molecule. You see, in water, nothing changed. No, there is no isomerization. And what we see is photobleaching and stimulated emission with some decay. So the behavior is relatively simple. In DMSO or in a sort of cell membrane environment, we see the appearance of the cis here and here, the cis absorption. So from this measurement, we could extract the kinetics, and now this is what Vituzzo. Our Vituzzo did this interesting global analysis, which is exactly what I show you. You see each, so he was extracted the cross-section and the kinetics. You see by global analysis, so you have two spectra. These resemble the cis absorption, the pink, and the blue is the more or less the trans, and you see the one goes into the other. And he was doing this for the three spectra. You see here the result. You see that the trans decay in about 6 picoseconds, and the cis is formed at the same time, and then they stay there long enough. So you see the time to rotate the molecule is in the order of 10 picoseconds. Then what I showed you before was the ensemble. The single molecule is very fast. In water, this doesn't occur. There is a totally different behavior, which is not associated to the cis-trans isomerization. Now, I don't want to go into the detail here, but I want to show you this as a last comment. It's a very special animation that I did for you. It's very complex. So one becomes narrow, the one becomes large. You see the time. So if the pulse becomes very short, the energy of the pulse is less and less defined, become more and more broad. So that means that if you want to study a phenomenon on 10 femtosecond time scale, you do not have the spectral resolution because the pulse is very broad. So you have to choose what you want to do. All right. So that's an interesting thing. The other thing is that when the pulse is very short, you can generate collective excited states. Let me give you this example. Here, we watch system things that are moving, obviously, but we do not see movement because the exposure time is longer than the transit time. So you lose the information of the motion. That would usually occur with vibration of the atoms. So you look at them on a time scale which is much longer than the typical vibrational period. You don't see them moving because you are averaging out this motion. You may see it in frequency space, but you don't see it in the time space. Now, how do they move? They move, say, the nuclei move at about 1 kilometer per second on distances which are in the order of a hundredth of nanometer. So that means that if you have a 10 femtosecond pulse, you are pretty much about there with the correct time resolution to see the motion of the nuclei. And then when you do experiment in a pump probe with such short pulses, that's what happens. That you see this fancy strange oscillation in the spectrum. Here I was taking away the steady state and keeping the oscillation. You see that there are oscillations. You see very well that there is an oscillating pattern. There is even beating. You clearly see the beating better here probably. You see the beating goes to 0, then back. Obviously there is more than one frequency. So what's going on here? Why we see this strange behavior? Well, if you do a Fourier transform, you see that there are specific frequency in the pattern that I show you, and those frequencies correspond to vibrational frequency of the sample. So these are Raman modes, well known, stretching, double stretching of the carbon, single stretching. So what is going on here? We are looking at vibration. Why? Well, because the time of the pump pulse is shorter than the vibrational period. So if you get to this regime, the coherence that you form is not just at equal 0 for all the phenomenon, but it's a real overall coherent state, even in a more subtle meaning. Let me tell you. Suppose you have a pendulum. You can excite it by a hammer which comes impulsively, and the interaction is much shorter than the oscillating period, and then this thing starts with a momentum. So you give a momentum to the pendulum and it starts to oscillate, impulsive excitation. Or you can displace the equilibrium position. That was happened most of the time in spectroscopy. So if you suddenly move the equilibrium position without moving the pendulum, then the pendulum finds itself out of equilibrium and it will start to oscillate because you were changing this without moving this. So that should occur again on a time scale which is much faster than the vibrational period. And we do this. We do this because our pulse is much shorter than the vibrational period. So we push and we kick the oscillator. But of course, you see the nuclei are not classical objects. So what I show you is a pendulum. Position and momentum are well defined, is a classical object. But nuclei are not classical objects. I'm almost done. So we need to enter quantum mechanics. And here I have a very nice slide by Z. Weil, Nobel Prize for femtochemistry, which is showing you that if you have a broad pulse, you do not excite just a single vibrational level, you excite many, and the superposition of material waves, this phonon wave, give you a wave packet, which is a quasi-classical object, which is a pendulum. A wave packet has a position and momentum, it's a pendulum. So now I can excite the pendulum and I can see the motion. Here you see better the equation. So what we do, we project the ground state wave function of the harmonic oscillator, a Gaussian, into the excited state, but in a different position. You see, I displaced the equilibrium position of the oscillator. And this displacement depends on the electron-phonon coupling. If the electron-phonon coupling is 0, there is no displacement, nothing is occurring. If there is electron-phonon coupling, the position here is different than the position here. And then when you go up there, you are out of equilibrium, and you get a Gaussian here, in the best case. That would be the total coherence, like the minimum uncertainty wave packet. And this Gaussian is moving like a classical object, because we know that the wave packet follow classical trajectory. So that's a pendulum that has been displaced by very short pulse. Of course, the pulse, Frank Condon, right, should be very short, and the spectrum should be very broad. Otherwise, I cannot excite all the level, because you see that I have many vibrational levels here. I need to excite all these vibrational levels at once. So this is the ground state. What we usually do, we measure, we generate phonons without any coherence. So we measure the number of phonons, but we do not measure any position, because the position average is 0. But if we generate a coherent state, then we can follow movement, and then the position can be measured as well. So the position is a collective property of the quantum oscillator through the wave packets, through the coherent superposition that allows you to study the motion of the system. All right. And that is a simulation that I did, one of my very few simulations in my life. It's the motion of the wave packet in the ground state, and it shows you the stimulated emission that you can measure. You see that now we are doing a non-stationary state spectroscopy, because what we generate is a non-stationary state because we built a coherence in the excited state. And this coherence is associated to the motion, no? So to the wave packet and the motion. All right, that was an example finally for the time resolution. Thank you very much for staying here.
Time for questions? Yes, please.
Thank you for the lecture. It was very interesting. With this technique, would you explore also direct transitions, like energy transfer dynamics?
Sure, energy transfer, you mean? Yeah, sure, you can, yeah. All kind of energy transfer, charge transfer, all kind of this kind of thing. You can, indeed, you can also add space resolution and go to different position with confocal microscope and see real motion in space. Most of the time you do in the phase space, so you measure energy, so you see energy transfer from one system to the other. Yeah, you can. It's a typical technique for doing this. Of course, you have this trade-off, right? If the energy, so I've been studying energy transfer that were comparable to the pulse and they were extremely fast, then it become tricky. And there are techniques that go above the limit I was telling you, like the 2D spectroscopy then it's able to not to beat the uncertainty principle, because that's not the case, but it can allow you to have high resolution and in time and frequency. Otherwise here you're in trouble because your pulse is very broad, right? So you excite everything.
So if we have no more questions, let's thanks again.